Yes, excellent. Okay, so hello everyone, and thank you very much for attending this session of the MDENet network. Just a few disclaimer before starting presenting the slides. So first of all, it's not a demo. It's not well prepared as it has been done for the previous presentation. So well done for the presentation, but there is no pre-recording and so on. So it will be completely live. And last but not least, it's even not a research contribution, but it's more a call for action. So you will probably leave more questions than entering in this session. And I'm most interested in having some interaction with you and having your feedback about the relevance of this call for action. So it's mostly raising a discussion in our community, in our MD communities, and providing any research contribution or even the presentation of a tool. So this being said, I'm going to discuss about scientific software and more specifically scientific computing and how software engineering and more specifically model-driven engineering can be a key enabler for the future of scientific computing. So, okay, software is eating the world, but more specifically, scientific software is eating the world. We can see scientific computing almost everywhere. So, of course, when we mention scientific computing, the first thing that we are thinking about is using scientific computing for understanding some complex natural phenomena, which is true. We use a lot scientific computing for trying to represent, understand, and even more about natural phenomena. So, for example, we did a lot of scientific computing related to COVID-19. We are doing a lot of scientific computing for understanding or trying to understand some phenomena related to climate change. So many areas in science where we use scientific computing. But scientific computing is not only for science, it's not only for understanding natural phenomena, but it's also used a lot in industry and more specifically for designing the future complex systems. So right now we are pushing some robot on Mars. We are providing very nice complex systems that are all designed initially by doing a lot of scientific computing. So when we talk about scientific computing, of course, there is scientific computing in science. And we mostly try to have some holistic view on very complex and wicked problems. And then we do some what-if scenarios, such as we can ask questions and do some prediction and try to understand this natural phenomenon. But we also use scientific computing in industry, specifically for designing complex systems. So very early in the development of the future complex systems. But we are also doing scientific computing when we operate the different systems, and more specifically in digital twin. As soon as we want to do some simulation or prediction, predictive maintenance, and so on, we use a lot of scientific computing for doing all these simulations. And last but not least, we are also using scientific computing for society in general, in the sense that scientific computing is not only used by scientists or by engineers, but they are also more and more used by decision and policy makers, such as they can take some societal decision. Which means that scientific computing is also more and more used by different stakeholders, and we have a broader engagement with our scientific models, and we can even use it for education and for better understand some phenomenon and increase and improve the education that we have on a specific question. So scientific computing is really everywhere and is eating the world. So what is exactly scientific computing? So at the heart and soul of scientific computing, we have computing capabilities, big machines, and we use these big machines for doing very big simulation and running a lot of simulation on those machines. So that's a complete research field. I mean, there is a very big field about high performance computing. And by the way, that has been the Turing Award of this year. And it's not directly related to our community. But on top of these big machines, Of course, we are building a lot of models, and this is where the model-driven engineering community can have some relevance with regard to scientific computing. We build a lot of models for understanding, so let's say descriptive models of scientific problems or engineering problems or even humanities problems. And we can even build some models for trying to solve those problems and to be more predictive. And here it's not anymore descriptive models, but more predictive, prescriptive model. And on top of this, we try to do more and more prediction, such as we can ask questions and see what will be the impact of a change on our natural phenomenon or a design choice in our design of future systems. And for this, we are also using predictive models. So there is a lot of models, but very different models from descriptive, prescriptive, and even predictive models. And all of these models are used in scientific computing. So if we look at these models, most of the time we start from mathematical models, and those mathematical models are most of the time continuous because the phenomenon that we are representing is a continuous phenomenon. We can also use some mathematical models that are directly discrete, such as agent-based models or such kind of models. But let's start from the most complicated situation where we have a continuous models, differential equation, for example. And we start from this, and at some point, what we want to do is to provide some scientific software that will run the simulation. And for this, in between the mathematical model, which is a pure representation of the continuous phenomenon, we need to do some discretization of these models up to the point that we are able to implement it, such as we can run it on our running infrastructure, such as for example, our big servers for high-performance computing. So there is a complex software development process, which not only start from directly discrete models, but possibly start from continuous models that we first need to discretize. So at the end of the day, if we look at the resulting scientific software, there is some specificities that can be interesting to understand before providing some facilities for scientific computing. Regarding the specificities of the software itself, most of the time, due to the discretization, it's at the end of the day a very highly iterative process. What I mean by this is that most of the time the discretization come up with a very big matrix, and then we need to iterate on this matrix for doing some computation. So it's super highly iterative, iterative on very large matrices. So we are processing very large data set as input. Most of the time there is complex compilation chain and deployment. It's not only running on our laptop, but it's to compile for very specific hardware. And then we need to deploy on those specific hardware, which are most of the time computers that are not easy to access. The lifetime of the application can be, in some situation, very long. And when we build these very complex models, we are maintaining these models over decades. So the lifetime can be very long. And last but not least, one of the specificities of this software is that the software is usually a mean and not an end per se. I mean, the end goal is to be able to understand, to solve, or to predict something, but the construction of the software is not an end per se, which has a very big impact on the stakeholders that are involved in the development process. First of all, the developer. The developer is rarely a software developer. It's most of the time a scientist or engineers or at the best numerical analysts. But they are not directly software engineers with good skills in software engineering and more specifically in model-driven engineering. The end user is also different in the sense that most of the time the end user is the developer itself. So a scientist or an engineer that develop his own software that he use afterward for understanding and predicting some situation. But it can be also other kind of stakeholders that are also beyond the computer science community. It can be the decision makers that use those models and the resulting scientific software for doing some prediction, or it can be also the general public that use it for increasing, for example, the education on a specific set of questions. And last but not least, again, the founders of the development of this scientific software, most of the time is found by third parties, such as institutional or governmental institutions. And most of these founders don't have any background on software development, which means that because the software is not a hand, but just a mean, and because they don't have a good background on software development, it's super difficult to put some effort on providing software of good quality. What I mean by this is that putting a lot of effort on a good design, on a good development, with a lot of validation and verification, and so on and so on. So if we look at the development process of this kind of scientific software, here on the figure, you can find the classical SE software engineering V model in green. And what we represent on this figure is that the software development process subsumes the classical software engineering V model in the sense that we start the well-known V model as soon as we have a numerical scheme. But before getting this numerical scheme, we start from mathematical models that we need to discretize into a numerical scheme. And even before these mathematical models, we build it from observations. So the development process subsumes the actual one that we have in software engineering. And it subsumes the ones that we know in software engineering because he also had new stakeholders. So it's a very multidisciplinary development where we have scientists, numericists, software engineers that have to collaborate for building this scientific software. It's highly collaborative. So we also know this challenge of the collaboration in software development more general. But here we also have this collaboration both in time and space. In time, because we are improving our knowledge on specific phenomena and we need to improve the representing models. But in space, because we also have different variants of the same models and we try to evaluate the differences and what will be the impact of these differences according to the different scenarios that we are representing. Which means that the mathematical models that we are building most of the time are highly configurable or even highly variable if we have different variants of these models. And of course, we use software languages and more specifically modeling languages for building these different models. And we need to be careful about the responsibilities in terms of language provider, but also in terms of language users, according to the kind of languages that we are providing. The more general purpose the language is, the more flexibility it will provide, but also the more rigorous engineering principles and validation and verification activities it will require. What I mean by this is that if we want to be highly flexible, of course, we can use C or even C++, very low level, where we can deal with memory, we can deal with concurrency, we can deal with many concerns, which are very computer science concerns. So we have a lot of flexibility with regard to these concerns, but we have a lot of responsibilities in terms of making sure that our model will be correctly implemented at this level of abstraction. And as we have said, the developer is most of the time not a software engineer, but someone with possibly no skills, specific skills in software engineering, which means no skills in validation and verification and so on. So most of the time they are keen to have this flexibility, such as they can improve the performance, for example, of the simulation by doing more concurrency and so on, but they don't have the right skills for making sure that they are dealing with these concerns in a correct way. And then we can have some more abstract languages. So the case of C++ on the figure on the right was bottom right figure, where everything has to be covered by the language user. And more abstract will be the language, or more abstract will be the concepts provided by the language. And more responsibility will be also put on the language provider. So if we provide, for example, a DSL, a modeling language that can be used directly at the numerical scheme level, of course, we need to ensure some guarantees about how this numerical scheme will be implemented in terms of concurrency, memory consumption, and so on and so on. So it's really a trade-off in between the level of abstraction of the software language that we are providing and the responsibility of both the language user and the language provider. So in terms of conclusion, the current momentum is that we have an ever-increasing intrinsic complexity of mathematical models. We are always trying to represent in a better ways the different phenomena, such as the mathematical models are more and more complex. We have a broader engagement of the stakeholders, not only software engineers, but scientists, numerical analysts, but also possibly domain experts, general public, and so on and so on. We have numerous scenarios. In the past, scientists was building their own simulator for themselves, such as they wanted to simulate the more precisely possible the phenomenon that they was representing. And now, because we open these models to possibly decision makers, to possibly the general public, and so on, they are using the models with different scenarios. So, for example, they want to have more interactivity with this model, such as they can do some what-if scenario very easily. But of course, they don't have days and weeks to wait for having the feedback. So it's really different. They want to trade off some precision with regard to some interaction and reactivity of the models. And of course, we want ever more efficient and large simulation. So it's a call for establishing the required software engineering foundation, tools and methods that we need for scientific computing. And the question that I'm asking to all of you is, what is the role of the MDE community for this? I'm personally convinced that because there is models everywhere, modeling languages everywhere, we should be part of the key enablers for supporting scientific computing. But right now, there is not so much done in our community, specifically for the scientific computing community. So it's really a call for action. I will go very quickly on this, but the opportunities is that there is an increasing demand. At least it's my personal feeling. Society is more and more driven by science. At least I would say that most of our political guides try to back up their decision with some scientific simulation. Let's see, for example, for the COVID-19, where most of the decision was taken based on the simulation of this or this of these models. So our models are driving some political decision, and it's super important to provide correct models. There is an acceleration of the natural phenomena that we need to understand if we want to cope with the very big challenges coming ahead. And if we want to do some breakthrough in engineering, we need some innovative thinking that will also require more flexibility and reactivity on the way we build and evaluate our scientific models. And in parallel of this, there is also an evolution of the technology, which is also acknowledging the fact that we can support in a better way scientific computing from the MDE community. There is a continuous evolution of computing capabilities. There is progresses on the modeling and simulation tools and methods. There is some breakthrough on the development environment. We talked in the previous talk about language servers, for example. And one of the key change in the past year is that we are more and more going to cloud infrastructure. I don't want to say web, but mostly cloud native applications, such as we can have an easy access from our browser to very complex tools that we are building. So it's a lot of opportunities, and for us, I think there is very important objectives to have these actions, such as having European leadership in the scientific community, but not only in the scientific community, also in industry. So if we want to keep the competitiveness of the European industry, and of course to have a broader engagement from our decision and policy makers, but also from the general public. I think that's it. I will skip this. And this is my last slide about the takeaway messages. So I think scientific computing is really important in science, engineering, and society, with some specificities, both of the software itself, but also the software development process for building this kind of software. Software languages are super important, and more specifically, domain-specific software languages, I would say modeling languages. We need to provide the proper abstraction. We need to provide languages for both descriptive, prescriptive, but also predictive modeling. And we need to support the coordination of these different kind of models. And I really think that the model-driven engineering community should focus on this, establishing a vision with an associated roadmap. I think it's really timely and relevant. It can be super impactful and a unique opportunity for our community. Thank you very much.